Hey everybody, this is lesson 2 of our first unit on atomic structure. So this is the lesson we did last week, and we're just going to go through a quick review here. So we're talking about the nature of light, particularly thinking about photons as these sort of units of kinetic energy. They're particles that never stop moving, and they have a lot of interesting aspects of them because when we look at these particles as a whole, as a group of particles, we find that they start to behave in ways that are more interesting, like behaving like a wave. So this is the example that we often refer to, which is the Thomas Young experiment. And in Thomas Young's experiment, he has also known as the double slit experiment. He took some light and he shone it through a single slit. So we can imagine this would look like this little doodle I've made down here. So we can imagine what he'd be looking at if he was looking at S1 here. The light is shining on the slit, and we would have this sort of, beam of light, a circle of light. And then when we look at the wall, at the pattern this light makes on the next wall, we could see that we would see this sort of the spread of light. So the light doesn't come out in just like a narrow band. It actually will spread out, and it even spreads out wider than you might even expect based on just this little tiny hole. If you were just firing like single particles, they might follow this little arrow here. And they could, sort of spread out into a range of spots there. But when we send, or if we were thinking about, something hard, like if we were thinking about little hard spheres or something, bullets is a good example. If you're firing bullets from a gun and they're firing into this hole, maybe they deflect a little bit off the edge and you can get like some spread, but the bullets would mostly land right in the center. And so we would expect if we were using, say, an electron gun or a photon laser, we would get a whole bunch of dots in the middle, and maybe they'd have a little bit of spread. So that's, it's not too surprising that that on this first spread, we get sort of a little light pattern. Maybe it's a little darker in the center, a little lighter on the sides. But the weird part happens when when the light passes through these next two slits. Instead of getting another pattern where you kind of would expect there'd be sort of a big, the expectation might be that, we'd have one circle of light here and we'd have one circle of light here, just essentially the same pattern. Then where those two circles are overlapped, we could kind of imagine there'd be like a darker circle. That would make more sense. But instead, what they observed was this weird interference pattern. I've kind of drawn out, what this might look like here. So little lines of light with bright spots and then dark spots in between. So we could even think about these are sort of darker lines or nodes, places of zero light. And so that's very peculiar. But if light was traveling in a wave, this is not unusual for waves to do, because in a wave you can have constructive interference where the two waves are matched, and then the wavelength, the amplitude would actually be increased, and that would account for these bright spots. So this would be a constructive spot. This would be a constructive spot. And then, meanwhile, if the two waves were opposite, my waves are really ugly here, so I'm going to try to draw an opposite wave, like so. And I'm going to draw this one to be even more opposite. Right? So if these were two opposite waves, let's put a little line through here and a line through here. Then when we add these two together, we get a deconstructive or a destructive interference. And so this would account for the dark lines that we're perceiving. And there are a lot more complicated versions of this and explanations, and feel free to explore those on your own time. What's really, really weird is with electrons, if we replace in the electron version of this experiment, or even the photon one where we can control single photons, and we fire them out one at a time, we do notice this sort of spread. So the first exit point, we would get a lot of dots right in the middle. So we'd have a really high density section of dots right here, because those are the ones that went straight out the hole. And then there would be a couple of electrons that kind of spread out from that point. And then out of the electrons that escape, that get through the actual slit, maybe I'm going to make my slits made of black here instead. The actual ones that make it through this next set of slits, they also have a little bit of spread, but they end up making sort of that same sort of bullet pattern of like dots and then some less and less dots. So we get, if we do these this pattern with, sorry, just one second, I'm just going to use a bigger. So we can kind of think that we get something that looks like this with a dark spot here overall, and then the same thing here. And so we would actually, the only spot of overlap would be this little bit of slightly increased chance of dots, or of detection of electrons in that center spot. But so from the side, you would get something that looks a lot more like this, with sort of radiating amounts of electrons sort of landing, kind of like a little target, right? All these would be, this is where the electrons would land if you're doing them one at a time, or even if the photons are going one at a time. They would land nearer the center, and then there'd be a couple in this area, and then there'd be a couple extra there because of they'd be coming from both circles, and then there'd just be a few in the outside edges. And so this is really weird, right? If you do this with single photons or single electrons, is the pattern you get is this bottom pattern. If you let all the photons loose and you don't watch them, and you don't watch the electrons, you get this interference pattern. So this is where the wave-particle duality kind of comes into play. So if we have to talk about waves, we have to talk about the electromagnetic wave. This is the idea that we can describe the movement we can describe the behavior of a photon as one of a wave passing through the electric field, and as that wave moves through the electric field, it causes a perpendicular wave to travel through the magnetic field. So that's the perpendicular wave. And so movement of electrons if you move electrons like in a current, you can actually create magnetic fields. This is how an electromagnet works. Is we move electrical charges, or electrical charges, electrons, move them, and in their movement they create a magnetic field. And light is made both of these electrical and magnetic energy, or electromagnetic radiation. So these photons can essentially carry both electrical or magnetic energy on them in a way. Now, I mean, at this point, we don't really have to go much farther into this. We really only care about electric fields because we're talking about electric charges, or electrons which have an electric charge. Magnetic components are really, really complicated and very specialized. There's very little application that we're going to do in this class that requires us to even think about magnets at all, and magnetic fields. Okay, so wave nature of light. You need to know this diagram, know the idea that there is a wavelength. It's the distance between two crests, or the distance between two minimums, or troughs, or the distance between two midpoints. And they have to be identical midpoints, so the line has to be moving in the same direction. And that's what we call a wavelength. The amplitude, one of the special features of a wave is that the amplitude has to be the same above and below the midline. And so that's what we're seeing right here. So both of these would count as the amplitude. Usually x is going to be time in our case, although it could be distance, and so, well, in this case it's wavelength, so it's time. The wavelength is demonstrating in distance. in this case. The frequency is essentially how many times in a single time period that we can go. If we're thinking about, in this case, a photon, which travels at the speed of light, then as soon as we know the distance, we also know how much time has gone by, because we know the speed as it's the speed of light. So we can look at the wavelength and think about, for a single time period, so this one I've got time down here, how many times is the wave repeating? So in this example, we have one repetition, or a period of one single wavelength inside of that time, or the wavelength is repeating once per second. So in this single second, we are getting one repeat. In the time below that, we can see a frequency of 2 hertz, where we have 2 repeats in the same time, and this would require that the wavelength be halved. So here, wavelength is half that of wavelength 1. Let's call this 1, and let's call this 2. Let's do that. So wavelength 2 is about half that of wavelength 1, and that's because the frequency is twice as fast. All right, we talk a lot about the, there's some interesting things to be thought about in terms of the actual spectrum this creates. Wavelength and frequency are interconnected through these equations, through the light equations we're going to cover in a second. On this page, the Planck's equations. And so as wavelength becomes shorter, the speed at which the photon is, switching phases and above and below the midline is increasing. That requires more energy, or it can be a way of representing more energy. So the faster your frequency, the higher the energy. And a great example is gamma rays. Gamma rays can actually pass right through you, right through solid matter, and if they are lucky or unlucky, they can interact with atomic nuclei, and they cause all sorts of problems, interfering with the function of the protons and neutrons and all those sorts of things. So gamma rays can be really nasty. X-rays also very strong, and also very high energy rays. They are very high energy, and they tend to interact with electrons that are very close to the nucleus, or very dense materials. So in the case of an X-ray, your arm is laying there, and why did I pick an arm? Now I have to draw it. And the X-rays, your arm is sitting on a piece of photo paper, or a reflective piece of paper is above it. Either way, and the electrons or the photons are flying down, and they will reflect off of, that's right, the piece of photo paper is above your arm, and they will reflect off of the bones, but they will pass through, they will pass directly through the softer material. So we get a bright spot where the bones are, and we get a dark spot where the meat or the muscle is. I believe, anyways, that's the general idea, is that your hard bones reflect it, and your softer tissues just let the X-rays pass through. X-rays typically have enough energy, and they can interact with atoms enough that they could cause ionization of electrons, and that could be damaging to things like your DNA. Over here in the radio side, these are the low energy side. And there are things like AM radio. AM radio is like 990, it used to be like 990 megahertz was, is that right? 990 megahertz? Anyways, AM radio is, I have to think about that. Anyways, I believe AM radio is the longer wavelength, and FM radio is the shorter wavelength. And the longer wavelength allows for less repetitions in an area, so the signal actually travels farther, but it can carry less information. And so AM radio typically sounds worse, and the FM radio is much faster repetition and carries more information. So here we go. I just looked it up. The AM radio is only 535 to 1605 kilohertz. Meanwhile, FM radio is in the megahertz. It's 88 to 108 megahertz. So it's actually a factor of 1,000. That's a pretty big difference, I would say. Well, not quite 1,000, but it's pretty big difference in frequency, you know. And this difference allows it to carry a lot more information in FM radio. Unfortunately, the high energy means that it bounces off of more things more often. It gets dispersed more easily and diffracted, and then that ends up dispersing the signal. And so FM radio channels can very often only reach, you know, a couple of kilometers outside of a city, or, you know, sometimes, you know, if you're in Kenora, you might get like a Power 97 or something, but you'll always get the AM radio stations, because the AM radio stations are a much longer range reach on them. Okay, so things we're looking for from this picture is that the longer the wavelength, the lower the energy. The shorter the wavelength, the higher the energy. The higher the frequency, the higher the energy. The lower the frequency, the lower the energy. As a very complete aside, this is only one model for it, this wavelength model, or this you know, the moving sine wave. You can look at the way that the photon, if you want to wrap your head around like, what is this looking like? Well, in the end, there isn't really a good explanation for that. There isn't a good way to think about that. There are good ways to think about it, but there are probably better ways. There are always better ways, or, you know, a lot of physicists will just say, just look at the math. The equations are all that matters. It doesn't matter if you can imagine it or not. So these equations work, and so the equations we're going to see in these Planck's equations, they work. They explain things. It works to explain things as a sine wave. That's what works. It will explain the phenomenon that we observe. That's unfortunately got to be good enough in a lot of these sort of quantum mechanical things. I'll show you just how weird it can be. There are many weird things you can use to explain what's going on. Feynman, who's a famous physicist, he described the photon, instead of describing it as a wave, he described it as a particle that sort of has some sort of arbitrary like direction. He called them little arrows, or he would draw these little arrows, and he'd say, okay, so imagine that the photon was just this little arrow thing, and this little arrow, as it moves through space, so the arrow is traveling this direction, it's traveling along this line, the arrow always has to rotate at a certain frequency, and the arrow just goes like this. Whatever this arrow is, it seems to have it behaves as if it was like the phases of a sine wave. But what I do like about this picture is that I found that when I was first trying to picture this movement, I was picturing the particle actually looking like a sine wave, but instead think about it more like a particle that is, you know, changing behavior as it moves. It looks more like a wheel kind of traveling around now to me, and it just kind of goes through all of its cycle. The wheel is always touching the ground, even though if you connect all the points, let's see if I can get it to do this, something like that. So even if you connect all the points, you get sort of a sine wave out of it. It's not my most beautiful sine wave. I have to think about what I want to do there, but that's okay. Anyway, so you get I'm going to try one more time just to satisfy. I probably should have drawn the sine wave first, and then I could have drawn the arrows to sort of match. But these little rotating arrow things, this could be your photon too. Your photon could be could it be a particle that has some sort of arbitrary little direction to it, and then as it travels through space, it changes direction as it moves. Maybe it's the laws of physics essentially are saying that it's in order to move, it must rotate that little arrow. So we can think of our photons as a bunch of little wheels, and faster, higher frequency photons, they spin their wheels faster as they move, and the low frequency photons, they spin their wheels slower. And the difference in that spinning wheel is what means, it's more energy to spin the wheel faster. So then if we had a faster frequency, I'm going to really regret drawing it that way, then you would have to think about it like a wheel that is spinning very, very quickly, going through cycles much, much faster. Can't do that because I can't draw that good, but that's kind of the idea. This is, let's just put this in a thought bubble because it's not really applicable, but it is just kind of trying to show you that these are thought experiments, or not a thought experiment. These are theoretical ideas to explain the universe as we observe it. All right, we can move on here. I'm seeing I have 26% battery life, so let's just keep going. So these are the equations we have. There's 3 equations. I'll show you how to use them. I think we've used them all in class already, so let's just get into it. So if we're going to calculate the energy of a photon, we can use the first Planck's equation, E equals hv. Here h is the Planck's constant. It is a unit that has joules in it and seconds. And so when we multiply that by a frequency, which is in per seconds, the seconds are canceled and we're left with just joules. Watch out with your exponents. If you're dealing with visible light, your energy should be 10 to the negative 19 joules. Okay. If you want to get more energy, one of the solutions is to just get more photons. So that's why light intensity is really important in terms of getting high energy reactions. So lasers are really good at getting something done because lasers are a lot of photons all working together, all compacted into a very narrow beam, and you get to add up or get to multiply this value that you have here. So the more photons you have, the more you get to multiply that value, and you can increase your energy up into ranges that are useful. 10 to the negative 19 joules is nothing, right? You need 1 joule to raise 1 gram of water by 1 degree. So 10 to the negative 19, you're going to need almost a mole of joules, a mole of photons, and you can start to do some really good stuff with that. Start to heat up water. Okay. The second one, we have a couple options. We can reorganize our C lambda V equation into this format. When you're writing your answers and your responses to questions, please try to include the version of the equation that you're using. So sometimes I see a student who just writes C equals lambda V, and then they actually end up using this equation, and it's confusing to the reader as to what you're trying to do there. Here we used angstroms, which are 10 to the negative 10 meters, and so that's the example there. Divide it out, we got 10 to the 14 frequency. That's pretty reasonable. The 10 to the 14 is about the visible range as well. This is where kind of studying this earlier image a little bit, you can see that 10 to the 14 is right in here. And then the wavelength is 10 to the negative 6 for wavelength, for visible light. All right, so here's a couple of questions I answered for us already. So the first one was about organizing. You can just look at the previous image. I always remember that red lights are warm. They even have like red light beds and things that you can go lay in instead of a tanning bed where it's just a warm light. And so that's red light. Also, humans and living creatures often emit in the infrared. We have night vision goggles that work on infrared light. And so infrared suggests smaller than red. So that would suggest that red is the lowest of the visible light spectrum. At the other end, you have the ultraviolet is really dangerous. That's what gives us skin cancer from tanning. And so then I always remember that if it's ultraviolet, which means above violet, then violet must be at the other end of that spectrum. And then I just fill in the rest with my memory of how the rainbow works and how color theory works. So I go red, and then red goes to orange, then yellow, and then yellow goes to green, then blue, and then blue goes to purple, to ultraviolet. Because at the very edge of blue is violet. At the bottom we have radio. Radio is the safest, right? Because we carry around phones that can access radio and microwave, so those are safer wavelengths. So those are down in the low energy. And then gamma rays is really dangerous. I always think about the Incredible Hulk, who was supposed to be made by gamma rays, which really would just have given him a whole bunch of cancer. But we have to suspend our disbelief, I guess, in some cases. But definitely are considered dangerous. So we can describe these relationships as frequency is proportional to energy, frequency is inversely proportional to wavelength, wavelength is proportional to the inverse proportion of energy. Okay, that's pretty boring. There is an electrical and a magnetic component to light. I'm not going to really get into that. This is a big hole. We don't want to get into that. All right, so here's another example question. We're given a wavelength in meters, and so we just punch this into the equation here. Use the E equals hc over lambda. You can see me dividing things out. It's a mercury lamp, so that's a lamp. It's something in our house that we can see. And look at that, we got 10 to the negative 19 joules, which we said was about the visible light range. Not much use to have a lamp that emits in a light range you can't see, right? Here's another example. We have calculate the energy and frequency of red light with a wavelength of 10 to the negative 6.45 times 10 to the negative 5 centimeters. So I did my conversion over here. Centimeters is to the negative 2, 10 to the negative 2. So then I multiplied 10 to the negative 5 times 10 to the negative 2, which means that I added the exponents. That gives me 10 to the negative 7. Punch that back into the equation. Cancel out the meters. Left with per seconds. Per seconds is the same as hertz. Now I have the frequency. And, even here I'm seeing that I don't even really like how I presented my answer. I really would have liked it if I had included the frequency is equal to 4.65 times 10 to the 14. And that would be in hertz. That would have been really good. I like it when you can be clear. Even here, I'd like to see an energy, and I would even like to see like a square. I think that would be helpful to do something like this. And put another one over here. That makes it so much easier for me as the reader to understand what's going on. Okay, let's do this last one on this page. We have the energy at this much value, so we can think that E is 3.11 times 10 to the negative 19 joules. And we also know that E is equal to HV, which means that E over H is equal to the frequency. So we might as well fill that out and give it a shot. 3.11 times 10 to the negative 19 joules divided by the 6.626 times 10 to the negative 34 joule seconds. Double check that these are going to cancel out. This is going to give me an answer that's going to be in seconds to the negative 1, because the seconds will be left underneath in the denominator. I'm looking at my exponents just to do some mental gymnastics here. I'm doing a minus 19 divided by a minus 34, so that's about, I don't know, I should be getting an answer in the 14s, I think. So let's see how we do. So 3.11 e. If you have these e functions on your calculator, they sure save you a lot of trouble. You don't have to write the times 10. You don't have to write a times in there. You just put the big E and then the exponent. And then I'm going to divide that by a 6.626. And I'm going to do again an E and a negative 34. This also saves you doing any brackets. The E will connect it to the first number, so you don't have to use a bracket. All right. Although feel free to use extra brackets. It never hurts to be prepared. Okay, so I get 4.69 times 10 to the 14, and that's in per seconds. This would be my frequency. So this is, so I don't have I'm not indicating my frequency, so I'm going to rewrite this just to make sure that it's clear. Times 10 to the 14 seconds, -1, or hertz would have been fine. Now I'm going to use my other equation, C equals lambda V, or V lambda, whatever. Rearrange C over my frequency equals my lambda. And let's do it. Times 10 to the 8 meters per second. Okay, I'll use that. Divided by 4.69 times 10 to the 14 seconds to the -1. Thinking about some cancellations here. Seconds to the -1 cancels the per second there. And I'm going to get an 8 divided by 14. 10 to the 8 divided by 10 to the 14. That looks like a -6-ish. Let's see how we do. 3.00. Don't really have to write those 00s, but why not? Divide by 4.69 e to the 14. Okay. Well, all right. -7. That's close to my estimation. 6.3. Now this says 965. Right? 965. I'm going to write that here, and then I'll clean it up on my final presentation. Looking back at all of my numbers in this equation, I always see that my original number had 1, 2, 3 significant figures. 3 digits are provided. Even my speed of light is 1, 2, 3 significant figures. So I should be trying to cut it off at 1, 2, 3 significant figures. That means that I'm going to have to round up, which is going to do a double round. So my final answer is going to be a wavelength of 6.40 times 10 to the -7 meters. So do please try to practice the good significant figures effort, and we'll continue to use that throughout the course and throughout your other courses for sure. And perhaps I'll go in and I'll fill in those other 5 questions there as we go. The last thing we did was the continuous spectrum. And so in white light, if you're familiar with your color theory, you know that the white light that comes from the sun actually contains pretty much every photon available. The sun is very, very hot, and it contains all the different types of photons. And then if we pass it through something that's got a different density than air, for example, water, we can split that white light and we can end up with something like a rainbow. Or if it passes through a piece of glass, you might notice a rainbow appear on your floor. That's because there is no way to make white visible light. So even when in a stage light, like we have in this little picture I've put in, the stage light is actually 3 different lights, one that's made of green light, one that's made of blue light, and one that's red. They're just using filters to get those 3 colors. And at the point where those 3 colors meet, you get white light. And so this gives you lots of options when you're working on a stage production or whatever, is you can blend the red, green, and the intensity of the red, blue, and green lights to get all of the different colors of the rainbow. But the most interesting part is that if you overlap the 3, our brains get confused and they see the color white. So this is interesting because when we start to do this, when we start to separate out the wavelengths that make up what might appear white, like our fluorescent bulbs in our house, in our classroom, when we separate them out using a spectrometer, our spectroscope, we notice that it is actually composed of 1, 2, 3, 4, 5 different bands of light, but none of them are white. And so we did the energy calculations for these bands, the violet, the indigo, the green, the orange, and the red. And then we compared them to a mercury discharge tube, which was known to be pure mercury. And we find that they are the same pattern. And this was our first indication that patterns of energy bands from a pure element are actually unique to that element. Here's the sun spectrum. You can see it's a continuum. I didn't quite get as good a spectrum as I was hoping, but that's okay. So this is called a line spectra, or an emission spectrum, or an emission fingerprint. And each of these lines is unique to that element. Sometimes elements will have lines that are very, very close to each other, but they will never have the same exact pattern. And this is where we moved from Rutherford's first Rutherford's original model to the Bohr model, because in Rutherford's model he had the electrons going around the nucleus as nucleus like electrons or planets around a sun, but this didn't account for the lines that we were observing in the line spectrum. Bohr realized that these lines must be equivalent to the energies that the electrons can have, and those energies must be quantized. And so that's where he decided that the orbital shells needed to be solid quantized values. So this is really convenient because we can now use this for identification. Here's a couple of identification questions we did in class. We take the mixture and we compare it to the fingerprints of the known fingerprints of the elements. These are our fingerprints. And when we compare them, we can see the barium line here, and another barium line here, another barium line, another barium line, another barium line, and another barium. Oh, no, this one is a lithium line. And so each of the lines in this mixture are from one or more of the elements above. And we can conclude that the mixture of gas that we're looking at is actually a barium and lithium mixture. We did this a couple times. We had a strontium, sodium, cadmium mixture. And this one over here, we can see this is a hydrogen and helium mixture. This might even be our own sun, or a star that's similar in age to ours, because our star is mostly hydrogen and helium. And you can observe these emission lines if you're very careful. We also did a flame test in class, and this is a similar process, but instead of using electricity like we do in the emission bulbs, we just use heat. And so you can see a couple examples. Here's some lithium in the Bunsen burner. It's a nice fuchsia color. Here's some sodium in the Bunsen burner, nice orange color. And here's another example of an unknown. You can match the lines, and you might look at these three lines and see how they're unique between the strontium and the unknown. So this unknown is strontium. Okay, that covers us for this second lesson, and hopefully you enjoyed this video, and we'll talk to you in a bit